Hello and welcome to this video on determining if a transformation is linear. So we saw in the last video, if you've been watching mine, the definition of a transformation and lots of terminology related to a transformation. Well, now in this video, we're taking a deeper look at a special kind of transformation. Transformation that is a linear transformation. What properties make a transformation a linear transformation? And then we'll go into several examples in which I'm going to determine whether or not a given transformation is one of these linear transformations. Okay. So the first page, just defining what it means for a transformation to be a linear transformation. All right, so a linear transformation is a transformation that preserves the operations of vector addition and scalar multiplication. And I'll explain what that means. It means that for all vectors, say u and v, these are representing any vector from the domain of T, right, from the domain of the transformation, and all scalars R. Now the scalars can belong to some field. Usually it'll be real numbers, the field of the real numbers. That'll be our set of scalars. But not always, but for the most part we're going to deal with real numbers as scalars. The following properties hold. One, and this is what I mean by preserving vector addition, the image of the transformation, the image of u plus v is equal to the image of u plus the image of v. And this is called in some texts the additivity property. Additivity, this first one. And again, when I say preserve vector addition, that simply means if you want to find the output for the sum of two vectors from the domain, you can either take the sum of those vectors first and then apply the transformation to find the output, or you can apply the transformation first to those two vectors and then add, and you'll get the same results. So that's what I mean here by preserving vector addition. And it also preserves scalar multiplication. So this is also going to be true if a transformation is to be called linear. The value of the transformation, the output for RU, right, scalar times vector u, is going to be equivalent to that same scalar times the image of u. So the image of RU is R times the image of u. Meaning that, again, the whole preserving scalar multiplication, all this means is that you can multiply the vector by the scalar first and then apply the transformation to get the output, or you can apply the transformation to u first and then multiply by the scalar and you get the same result. Right? It's preserving scalar multiplication, and this particular property is sometimes referred to as the homogeneity property. Okay, homogeneity and additivity are things that need to hold true for a transformation to be considered linear. Right? So every linear transformation is a transformation, right? But not every transformation is a linear transformation. And we'll see that in the coming examples. So the rest of the video, I just have examples of transformations, some called T, some called S, some called Q. Right? They don't always have to be T. It's just most times when properties are shown or definitions are shown for things involving transformations, they'll use the letter T because, T for transformation. So in the rest of the video, I've got examples where I'm given a transformation, and then I'm asked to determine if that transformation is linear. Are these additivity and homogeneity properties true for that transformation? Does the transformation preserve vector addition? Does it preserve scalar multiplication? All right, so let's take a look. So my first example, I have a transformation here from R2 to R2, a transformation between these two-dimensional Euclidean vector spaces. And here's the rule for the transformation, right? T takes a vector from R2, something with two components, x1, x2 for my input, and the output is also from R2, right, the codomain, and it's got components x1, and the second component is always 1. All right, and the question is, is this particular transformation a linear transformation? All right, so I'm going to show those, see if those two properties hold. Now, in order to show that a transformation is linear, both the additivity and homogeneity properties have to be true. If either one of them fails, it's not linear. All right, and and to show that they're true, you have to show it's true for every vector and every scalar. To show that they're false, you only need to find one example showing that they're false. Okay, a counter example, if you will. All right, so as with the page, right, as with this page, the first page here, the definitions, see how in these properties I have two vectors. I have vectors, two general vectors from the domain and a general scalar being represented in those properties. So that's what I'm going to have start off with here. So I'm going to let say u be some general vector from R2, which maybe have components u1 and u2. Right? And another vector v be another general vector, again, just using letters here. I'm not using specific numbers. Right? I want to make sure that this is true for all vectors from the domain. So say v is another general vector from the domain R2. So v has this look to it, and say these components are v1 and v2. So these belong to the domain R2. And suppose, again, I'll just use like lowercase r belongs to the reals, and this is a general scalar. All right, this is a scalar. And these are vectors from the domain. All right, so first let's take a look at that additivity property. All right, first let's take a look at, is the value of this transformation t at u plus v equal to the value of t at u plus the value of t at v, almost as if you're distributing. Don't think about it's not really distributing the t, but you can think of it that way. All right, it's not exactly distributing. All right, so let's see. So I'm going to start with the left side here. All right, the t of u plus v. All right, now in this one I'm going to add the vectors first. Okay, I add the vectors first, and it's vector addition. Again, I'm working under standard operations, standard vector addition and scalar multiplication in Euclidean space. So this will be t of, and when I add u and v, u1 u2 plus v1 v2, I would get this vector, with components u1 plus v1 and u2 plus v2, right, under standard addition. And then, so I'll add the vectors first and then apply the rule. Now, according to this rule, right, when I plug in a two component vector, the output has the same first component. So the output here has the same first component, u1 plus v1, but the second component is 1, no matter what these two are, right? So the second component is 1. So this would be the output when I plug in u plus v to the rule t. All right, so that's working with the left side of the equation. All right, maybe I'll just write left side here, left side. And then working with the right side, see if we get the same expression. And if we don't, if they're not the same, then maybe then we should come up with a counter example. Right. So the left side was where I apply the transformation to the vectors separately and then add them. So what's t of u plus t of v? All right, so that would be t of, and then u is the vector that u1, u2. And then I'm adding to this t of v, which is vector with the components v1 and v2. And I apply t to u first. Now remember, this would just be u1, 1. Right, applying this rule to the vector u1, u2. You just have u1, 1. Plus, and then applying the rule for t to vector v, v1, v2, I just have v1, 1. And then again, I'm doing standard operations here. Standard addition for vectors in R2. This would be the vector u1 plus v1. So great, it's got the same first component as that left side had when I computed the left side. But then look, 1 plus 1 is 2. So the second component of this vector, for when I compute the right side, is not the same as the second component on the left side, right? These are not going to be the same, no matter what you plug in. So I'm going to show that this is false. I mean, you could probably stop here and most people would understand that no, the answer to this question is no. Right, the answer to the question is no. So this transformation t is not a non-linear transformation. But I would like to also give a counter example to this, something with some specific numbers in it, right? In order to show that a general statement is false, you only need to show one counter example. All right, so it seems to me that this was going to be false, right? So here's a counter example to statement 1. Suppose I let u be. Now I'm going to a specific example. How about the vector 2, 3? Right, that's from R2. Why not? And vector v, say, is the vector 1, 1, 7. Doesn't matter. Right. Now t of u plus, again, I'm working on this, the left side. T of u plus v would be t of the vector 3, 10, which, if I apply this rule, would be the vector 3, 1 as an output. Right. And then if you look at t of u plus t of v, that would be, I'm just going to write what t of u is, right? T of 2, 3, when I apply t to it, would be 2, 1. And when I apply t to v, would be 1, 1. Remember that the first component is the same, the second component is always 1 in the output. So I'm getting the vector 3, 2. And these are not the same again, right? So we're seeing that t of u plus v is not equal to t of u plus t of v for all u and v in the domain, right? For all u and v in the domain R2. So that tells me the additive property does not hold, therefore t is not a linear transformation. All right, and in future examples, I'm just going to put is linear or is not linear and cut out the word transformation. Just to, it's implied that transformation is there. Great, and that so I don't have to continue. I do not have to check that homogeneity property. All right, so let's move on. So that's not linear, that first example. Next example. Here I have a transformation called S this time, right? In the past video, last video I made on transformations, and this video, so far, every transformation has had the name of T, but it doesn't have to be that way. You could call it whatever you want, right? This is S. So here's transformation S from, again, R2 to R2. I have other examples where the domain and codomain are different. Actually, this is an operator. Remember, when the domain and codomain are the same, it's called an operator. So I have this operator S, and it takes a vector from R2, right, with two components, this time X and Y, and maps it to, assigns it to the two component vector, another thing from R2, right, X, Y squared. And the same question, is this a linear transformation? So just like before, I'm going to grab have two vectors u and v that are representing just general vectors from the domain. So u is a vector from R2. So again, I'll just call them u1, u2. And another generic vector, general vector from R2, v, again, v1, v2. Right, so these belong to the domain R2. And again, R belonging to the reals, being a scalar. Right, this is just a generic scalar here. All right, so first I'll check, again, I'll check that additivity property. So the question is the value of this transformation S at u plus v equivalent to the image of u, S of u plus the image of v. All right, so just as I did in the previous example, I'm going to work with the left side, and we can't assume they're equal, right? I can't set these equal to each other. I don't know that they're equal. So I'm going to work with one side at a time and then see if they actually end up being the same thing. So the left side, I'll just put ls for left side. S of, vector u plus v, the sum of so this is where I'm taking the sum first and then applying transformation S, or operator S to it. So this would be S of, and again, standard addition here. So u plus v would be the vector, u1 plus v1 again for the first component, and u2 plus v2 for the second component. All right, and then applying this operator to this vector. Remember, so the first component stays the same in the output. So u1 plus v1. The second component in the output is the second component of the input squared. So the quantity u2 plus v2 squared. And if you'd like to multiply that out, which I will do here, that's u1 plus v1 for the first component. And then when you square something, remember, don't distribute powers. Right, that's u2 plus v2 times u2 plus v2, and you FOIL. So that'd be u2 squared plus 2 times u2 v2, and then plus v2 squared. Right. There. Okay. So that's my resulting output when I plug in u plus v to operator S. Then working with the other side, the right side, RS for right side, what's the value of S at u plus the image of v, the value of S at v. Okay, so this time u is this u1, u2. I'm just going to apply the rule. So what's S at u? It would be u1 for the first component, and then u2 squared for the second component. All right, plus, and then what's s at v? That'd be, I plug v1, v2 into s, I get v1 for the first component, and then v2 squared for the second component. And then adding these together, standard vector addition in R2. First component u1 plus v1. Second component u2 squared plus v2 squared. And notice how these expressions, now the first components are the same, but the second components are not necessarily going to be the same because of this extra term here, right? The 2u2 v2, that's extra. So these are not always going to be the same. So it looks to me though as though, now again, you can stop here, I'd be cool with that, just showing that these aren't the same expression, right? These really don't result in the same vector, the same output. But I would like to also, I'm going to show a counter example, right? Just to really hammer it home, show that this additivity property does not hold here. And I want to set it up too so that this is not 0, right? The 2u2 v2. So basically, as long as u2 and v2 aren't 0, either of them, this middle term here will not be 0, and then they're definitely not going to be the same, right? Because if this were 0, then these two expressions would be the same. But remember, this property has to hold for every vector u and v, right, from the domain. So I'm just going to pick some vectors here where the second components of u and v aren't 0. Alright, so here's a counter example to show that, property 1 does not hold. So I'm going to say, let's let u be the vector, 1, 1. The second component is not 0. And vector v, I don't want the second component of this one to be 0 either, to show that this won't end up being the same. 2, -3, why not? Okay. Alright, so let's look at what's s, the value of s at u plus v. That's the value of s at the vector, u plus v is 3, -2. So that output would be 3, 4. Right? Because remember that we're applying the rule, same first component, and then the square of the second component, so -2 squared, +4. And then what's s, so that's the left side, and what's s of u plus s of v. All right, well, s of u would be 1, 1 again. All right, first component, the square of the second component, plus then s of v would be 2, 9. All right, and then adding these together, 3, 10, and you see that these are not equal. 3, 4 is not the same as 3, 10. So we are seeing here that s of u plus v is not equal to s of u plus s of v. All right, so the additivity property does not hold. Vector addition is not preserved for all u and v in the domain, right, belonging to R2. Some of them will, right? This will be equal for some of them. Like I said, if u2 or v2 are equal to 0, then these will be equal because you'd have just u2 squared plus v2 squared. But it has to be true, remember, for all the vectors from the domain. So this tells me yet again that S is not a linear transformation. All right, so I've given you a couple examples here where where we have something that's not a linear transformation. Well, let's I'm hoping to come across one that is. Right? Now, again, since I showed the additivity property doesn't hold, I don't need to go into the homogeneity property. Okay. Next, this is transformation Q from vector space R3 to vector space R. So my inputs are vectors with 3 components. My output's just a real number. Right. You could say it's a vector with 1 component, but usually vectors with 1 component aren't written that way with the vector notation. Just write the number. All right. So my input. So here's the rule: Q of x1, x2, x3 is 2 times the first component minus the second plus 5 times the third. And get that this is a real number over here, one component vector, if you think about it that way. All right. So same deal. The question is Q a linear transformation? So just as before, I'm going to take just two generic vectors, 2 general vectors from R3. Again, I'll call them u and v. But they're from R3 this time, so I got components, say u1, u2, and u3 for vector u, and another vector, say v, which is v1, v2, and v3 components. All right, these are 2 vectors from the domain, and a scalar, r, lowercase r belonging to the reals, right? A generic scalar. All right, so now let's check that additivity property. Is the value of q at u plus v still equal to the value of q at u plus the value of q at v? All right, does this transformation called Q preserve vector addition? All right, so as I did with the last 2 examples, again, you can't set these equal to each other right now. You don't know that they're equal. So let's work with the sides separately. So the left side. So Q of u plus v. That'd be Q of, and then when you add u and v, again, standard addition, you have u1 plus v1, u2 plus v2, u3 plus v3. All right, and then popping that into applying the rule for q. Right, the output is 2 times the first component, right? So 2 times u1 plus v1 minus the second component, so minus the quantity u2 plus v2, and then plus 5 times the third component, right? So plus 5 times the quantity u3 plus v3. And if you'd like to simplify that a tad, distribute and get rid of parentheses, that's 2u1 plus v1, 2v1 minus u2 minus v2 plus 5u3 plus 5v3. Okay. And you're going to see that if I gather the u's together and the v terms together, this is going to end up working out. But I'll just keep it that way, and let's work with the right side. What's the value of q at vector u plus the output of the image of v, right? The value of q at v. All right, so I'm just going to jump to the results here. The value of q at u, right? So u is this vector. I plug this into q, and I'm just replacing x1 with u, x2 with u, x1 with u1, x2 with u2, and x3 with u3. So the value of q at u is 2 times u1 minus u2 plus 5u3. All right, that's the value of q at u. And then I'm adding to this, and then the value of q at v, plug v in here, the v1, v2, v3. I'm just replacing x1 with v1, x2 with v2, x3 with v3. So it'd be 2v1 minus v2 plus 5v3. And do you see how these are the same? Look at this, 2u1, 2u1. Negative u2, negative u2. I'll underline them. Got those, 5u3, 5u3. 2v1, 2v1. Negative v2, negative v2. 5v3, 5v3. And all terms are accounted for. These are equal. Right, and it didn't matter what u1, u1, u2, u3, v1, v2, v3 were any real number. So that means that these are going to be equal no matter what I replace u and v with, right? So no, for any vectors from R3, for any vectors from the domain. All right, so this is telling me that yes, q of u plus v is equal to q of u plus q of v for all vectors, for all u and v in the domain belonging to R3. All right, so the additivity property holds. Now, this doesn't mean that the transformation is linear. This is just part one, right? You have to show both those properties, that additivity and homogeneity, to show that a transformation is a linear one. So, next question. So, part two. Now I'm working on finally this homogeneity property. The question is the value of q at a scalar times a vector from the domain r times u, is that equal to that same scalar times the image of the vector? So is q of ru equal to r times q of u? All right, so same thing as before. I can't assume these are equal. I can't set these equal to each other. I don't know that they're equal. So I'm going to work with the sides again. All right. So left side. All right, we'll look at what's the value of q at the scalar multiple of u. All right. So again, standard definition for scalar multiplication here. I'm not changing the definition in Euclidean space. So what's r times u? That would be the vector r. Multiply each component by r. ru1, ru2, ru3. And then I apply the rule q to this. And remember, it's just the output is 2 times the first component, so 2 times ru1 minus the second component, so minus ru2, and then plus 5 times the third component, so plus 5 times ru3. All right, so that's what I'm getting. That's as simple as it gets. There's no parentheses or whatnot. Nothing to distribute. But there we go. All right. Now, if you want to look at the right side, rs, what's the value of r times q of u? All right, so that would be r times, and then in parentheses here, whenever you replace something, right, you usually put parentheses around it or brackets. Q of u, right, so if I applied q to u, this u1, u2, u3, I'd get 2u1 minus u2 plus 5u3. And can you see how these are actually going to be the same? Right, because all I need to do to simplify this is distribute the r. These are real numbers here. I can distribute multiplication over addition. So this would be 2, and then it's also commutative. So r times 2 times u1 is the same as 2 times r times u1, right? Multiplication is commutative with the real numbers. Real numbers are a field. So this is 2 times r times u1 minus r times u2, and then plus r times 5 times u3. Again, you can commute and say 5 times r times u3, so plus 5 times r times u3. And look at these, right? 2ru1, 2ru1. Negative ru2, negative ru2. 5ru3, 5ru3. All terms are accounted for. They are the same expression. They are equal. And it didn't matter what my u1, u2, and u3 were. They could be any real number I want. So this statement is true. This statement is true. The answer is yes for all vectors from the domain and all scalars, right? It didn't matter what r was either. So this is telling me that q of ru is equal to r times q of u for all vectors in the domain, so for all u belonging to R3, and for all scalars r belong to the reals. Wonderful. Now, since both the additivity and homogeneity properties are true, right? since both of them hold, this transformation Q is what they call a linear transformation, right? So it is linear. Wonderful. Okay, moving on. Next example. All right, so here, got an operator, right? The domain and codomain are the same. I'm just going to, but you see I'm doing the same thing every time, right? When asked, is this transformation or operator a linear transformation or linear operator? Here, my inputs are vectors with 3 components. My outputs are vectors with 3 components, right? Both from R3. So T of, x, y, z equals, x plus y for the first component, x minus y for the second component, and then just the same third component as the input, z. And same question, is this a linear operator or a linear transformation? All right, so start off with, again, I'm going to pick 2 generic vectors and a general scalar. I'll call them again u and v. So say u is, again, a vector from R3. U1, U2, U3 components, and vector v has components v1, v2, and v3. Again, both from the domain, the R3, right? And R, right, lowercase r again, just be a scalar, right, belong to the reals. Okay, so these represent any vector from the domain and any real and any scalar. All right. So the additivity property. All right, now this time I'm not going to ask the question. I'm not going to write the question. I'll ask the question out loud. Is T of u plus v equal to T of u plus T of v? All right. So I'll look at the left side. T of u plus v. Okay, that would be T of. Right. Again, this is where I'm adding the vectors first. The sum would be u1 plus v1. u2 plus v2, u3 plus v3. Okay, and then the result, then I apply the rule for t. All right, so I get this, again, a vector with 3 components. See, the first component in the output is the sum of the first 2 components of the input. So it's u1 plus v1 plus u2 plus v2. And I guess you could also put parentheses around these, but it's just a bunch of addition. So first component plus second component. If you want to put parentheses around, fine, but really they're not needed. Then see, the second component of the output is the first component of the input minus the second component of the input. So u1 plus v1, then minus, now remember this is minus the entire second component, so minus the quantity. If I would put this in parentheses, but if I distribute the negative, that'd be minus u2 minus v2. Do you see that? I hope, right? This is minus the entire second component, so minus this, minus that. Right. And then you see the third component of the output is the same as the third component of the input. So the third component here is u3 plus v3. All right, and that's as simple as that gets. No like terms can be combined in any of these. All right, and I got these 3 components. All right, then looking at the other side, T of u plus T of v. Well, again, I'll just apply T to u first. Right, so u1, u2, u3 applied here. I'd have u1 plus u2, and then u1 minus u2, and then u3. Right, if I apply the rule T to just vector u here. And then I'm adding to this, what's T applied to v, right? So v1, v2, v3 instead of x, y, and z. So it'd be v1 plus v2, v1 minus v2, and v3. All right, and then putting these together, I have u1 plus u2 plus v1 plus v2 for the first component, and then u1 minus u2 plus v1 minus v2 for the second component, and then u3 plus v3 for the third component. And look, compare the components. first components, they both have u1, they both have positive u2, positive u1, positive e2. So the first components are the same. Second components both have u1, negative u2, see that? Positive v1 and negative v2. So the second components are the same, and then u3 plus v3, same third components. These indeed are equal. All right, so I'm not going to write all that sentence out saying like, hey, so this, right, t of u plus v is equal to t of u plus t of v, right? Vector addition is preserved for all vectors u and v in the domain. All right, so I'll put like a check on that, right? Good, yes. So now I'm not done though, right? Just because the the additivity property holds, now I must check the homogeneity property. All right, so step 2. Look at t of r times u first, right? And is this equal to r times t of u, right? Can I basically pull the scalar out and have it still be equal? Does it preserve scalar multiplication? All right, so this would be t of the vector, when I do r times u, scalar r times vector u, that'd be components ru1, ru2, ru3. All right, and then I apply rule t to this, and I get another 3 component vector with ru1 plus ru2 for the first component, ru1 minus ru2 for the second component, and then the same third component, ru3. All right, so keep that in mind, and that's as simple as that gets, right? No parentheses or whatnot, nothing, no like terms to combine. Okay, and then the other side of this would be, okay, what about r? Take that scalar r and multiply it by the image of u, t of u. So this would be r times, and then t of u would be, you saw it earlier, u1 plus u2 for the first component, u1 minus u2 for the second component, and then u3 for the third component. And I multiply each of these by r. So this would be r times that first component, u1 plus u2, r times the second component, u1 minus u2, and r times that third component, u3. And do you see how they're the same? Distributing, right? If I were to distribute the r here, these are real numbers, so I can distribute, there is a distributive property of multiplication over addition. See how this would be ru1 plus ru2 for the first component, same. ru1 minus ru2, same. ru3, same. So these are equal. All right, so check on that. Right? We got the homogeneity property also holds. So since both properties hold, the additivity and homogeneity, vector addition and scalar multiplication are both preserved by this operation, by this transformation or operator, sorry. T is linear, is a linear operator, you could say, because the domain and codomain are the same. But we'll just say linear transformation, right? So T is a linear transformation. Wonderful. All right. And this is my last example. All right, so we've seen a couple that weren't and a couple that were. And don't be fooled. All right, let me show you the ones that were. All right, these were the operation. These two here, the Q and the T, where my fingers are, my pointer finger and my thumbs. These were linear. And look at the outputs. See all the variables, all the input variables, x1, x2, x3 here, were to the first power, and they weren't in denominators, right? There weren't any variables in denominators. There were no. They're to the first power. Every single term has a degree of 1, right? There's no product of variables. There's no x1 times x2. This is one variable, one variable, one variable. And there are no constants, right? There's no +5 at the end or +7. Something without a variable. Same thing in all 3 of these components. So each variable is to the first power, right, x, y, and z here. Each term of each component has a degree of 1, right? There's one variable in each term. There's no like x, y term. There's not more than one variable in any term. And there are no constants. There's no like z plus 4 or z minus 8. Right? There's no terms without variables. So you'll see that when your outputs look like that, your outputs have components where all the input variables are to the first power. There aren't any variables in denominators. There aren't any constants being added, and every single term you see has just a single variable in it to the first power. You'll be pretty you'd be pretty good at guessing that that was a linear transformation. If that stuff isn't happening, if there are variables in denominators or variables to powers other than one, right, square roots of variables, variables to the second, third, fourth power, fraction powers, if there are constants being added or products of variables, you can be pretty good at guessing that that transformation is not linear, right? So like, look at this one here. See how I had this, sure, the variables are to the first power in my output here, and every term with a variable only has one variable, but see this constant here, the +3, that's kind of a giveaway to me to tell me that this is not going to be a linear transformation, and we'll see that as we go through. Okay. So here I have a transformation from the reals, right, the real numbers to the R2. So my input is just simply a real number x, and my output is a vector with two components, right, something from R2. So t of x is, the first component is whatever the input is, and then the second component is the input +3. Alright, so I'm going to let, say, u, and again, I'm not going to put the vector number up here. Just going to say u, again, when it's just R1, when it's just R1, you really don't need vector notation, right? A vector with one component is just a real number, just a number. So I'm going to let u and v belong to R, right? These are general vectors from my input, right? From my domain, sorry. And this is a scalar, right? I know they're both from R, but these are my vectors, u and v, right? The things from the domain, and this R here is a scalar, right, from the field of real numbers. All right, so first, the additivity property. All right, so what's t of u plus v here? Let's see if I apply this. I do u plus v, whatever that is, and replace x with u plus v. So this will give me the vector u plus v for the first component, and then u plus v plus 3 for the second component. All right. Now look at the other side. What's t of u plus t of v? Well, t of u would just be, u for the first component, u plus 3 for the second component. Right. Plus, and then t of v, just replace x with v, would give me v for the first component, and then v plus 3 for the second component. And then when I do vector addition here, I'm getting u plus v for the first component, and then u plus 3 plus v plus 3, that'd be u plus v plus 6, all right, because you got the 3 plus the 3 there. That's u plus v plus 6 for the second component. And can you see how these are not the same? All right, these are not equal. So it's telling me that this is not linear, right? And I'll give a quick counter example. Just give me, here's two vectors. Say u is the number 3 and v is the number 5. Again, these are from the domain, the real numbers, just one number. So t of 3 plus 5, well, if I add the vectors first, that's t of 8, and the resulting output would be the vector 8, 11, right? 8, 8 plus 3. But t of 3 plus t of 5, right? T of 3 would be the vector 3, 6, right? 3, 3 plus 3. Plus, and then t of 5 would be the vector 5, 8. Right, again, 5, 5 plus 3, replacing x with 5. Adding these two vectors together gives me 8, 14. Right, which is, again, not the same. These are not equal. So we're seeing that t of u plus v is not the same as t of u plus t of v for all vectors in the domain, for all real numbers in the in the domain there. So again, you don't need to move on to the homogeneity property. Now there are going to be some, you might come across some examples where the additivity property holds, but not the homogeneity property. Just know that those are out there. I haven't really shown you one here. I'm sorry. But just know that they're out there. Right? There are some transformations you're going to come across where one property holds but the other one doesn't. Right? Or both properties don't hold. You know, the ones I've shown you so far, both properties actually wouldn't hold. But just be careful. Just know that there are some out there that have one property hold, both properties hold, neither property hold. Right? You're going to come across all sorts of things when you practice. But yeah, so definitely here, this transformation T is not linear. Wonderful. All right, so again, just pretty easy. Given a transformation, asked if it's linear or not. Assign some expression to two generic vectors from the domain, right? Like I've been calling them U and V this whole time, right? So assign two generic or general vectors from the domain. Assign, an expression, some like the lowercase r. Assign an expression to represent a general scalar, right, or general real number. And then you're checking, is T of U plus V equal to T of U plus T of V? Is the image of the sum equal to the sum of the images? And is T of RU equal to R times T of U, right? Is the image of the scalar multiple a scalar multiple of the image? If you want to say it that way, those ways. And if you do find out that they're not holding, right, if one of the properties doesn't hold, then you should probably also give a counter example just to really be safe, right? Show for certain this property doesn't hold for every vector in the domain or every scalar. And I would actually prefer seeing that, right? If you're showing that a property, a general statement doesn't hold, give a counter example. You should be able to. All right. Okay, so I hope you enjoy practicing problems of this nature, and thank you very much for watching.